All right, we're diving deep today, ready to tackle some pretty heavy mathematical lifting.
Oh, absolutely. Sounds like our listener is up for the challenge.
This deep dive, we're taking on Petz-Rényi relative entropy, specifically in quantum field theory.
And we've got a fantastic guide for this journey, a paper by Markus B. Fröb and Leonardo Sangaletti.
It's a fascinating paper that delves into some pretty complex stuff, but it's worth it, right?
Absolutely. The payoff is huge. It gives us a deeper, more nuanced understanding of quantum states.
It really builds upon some existing work, particularly the Araki-Uhlmann formula.
Right. The Araki-Uhlmann formula, it's our starting point. It gives us a way to think about the information content of quantum states.
Okay, so can you remind us what exactly the Araki-Uhlmann formula tells us? Just a quick refresher.
Sure. Essentially, it provides a mathematical tool to compare the information content of different quantum states. Think of it like a ruler, but for quantum information.
A quantum ruler. I like
Yeah.
that. But this paper goes a step further, right?
Mm.
Introduces the Petz-Rényi relative entropy.
Exactly. The Petz-Rényi relative entropy, it's like a more powerful, more flexible version of the Araki-Uhlmann formula.
More powerful. How so?
Well, it introduces a parameter, alpha, that lets us adjust the sensitivity of our measurement. By tweaking alpha, we can zoom in on different aspects of the differences between quantum states.
So it's like having a microscope with an adjustable lens. We can get a clearer picture at different levels of detail.
Exactly. And that's crucial because the paper highlights that the Araki-Uhlmann formula gives us just a partial picture.
Partial picture. What's missing?
The Araki-Uhlmann formula gives us the overall difference, the total information difference between states, but it doesn't tell us how that difference is distributed across different properties, like energy level.
Ah, I see. So it's like knowing two cities have different populations, but not understanding the age demographics of each city.
That's a good way to put it. And this is where Petz-Rényi relative entropy shines. It allows us to dig deeper into those finer details.
So it's like having a census for our quantum states.
You got it. It helps us understand the intricate structure of those differences, not just the overall magnitude.
Now, to do all this, the paper introduces a lot of mathematical heavy lifting, starting with something called the relative Tomita operator.
Right. The relative Tomita operator, it's a crucial player in all of this. It's defined as the closure of a specific map, as you can see in equation 2.1.
Equation 2.1. Okay, got it. Now, for those of us who aren't fluent in operator theory, what exactly does this definition tell us?
Well, think of it this way. The relative Tomita operator captures the relationship between two quantum states, and this definition ensures it has the right mathematical properties to do so.
Okay, so it's kind of like a mathematical tool specifically designed to probe the relationship between two quantum states.
Exactly. It lays the foundation for understanding how they differ from each other.
And then they take this operator and perform what they call a polar decomposition.
Right, the polar decomposition. It's a mathematical technique that allows us to break down this operator into two parts.
Two parts. What are those?
The first part is called the relative modular conjugation, and it's represented by the symbol J with the subscripts psi and phi. This part is a unitary operator, meaning it preserves probabilities.
In the second part.
The second part is called the relative modular operator. It's denoted by the symbol delta, again with the subscripts psi and phi. This part is a positive operator, which is crucial for defining the relative entropy.
So we've broken down the relative Tomita operator into these two pieces. But how does this help us with understanding relative entropy?
Well, the relative modular operator, the delta one, it's the key here. The spectrum of this operator, meaning the set of its possible values, gives us a detailed picture of how the information content differs between the two quantum states.
Okay, I'm starting to see how this all fits together, but this is just the beginning, right? They go on to prove various properties about these operators and the Petz-Rényi relative entropy itself.
Absolutely. They establish some key properties, things like non-negativity, monotonicity, and the fact that a certain spectral integral, which is important for defining the entropy, remains bounded.
So they're essentially making sure our mathematical tools are behaving properly, giving us sensible results, right?
Exactly. They're establishing the mathematical groundwork, ensuring that everything is logically sound and consistent.
And once they've laid that groundwork, they dive into a specific example, a free scalar field, in a region of spacetime called a Minkowski wedge.
Yes. The Minkowski wedge, it's a specific region of spacetime with interesting causal properties. Choosing this specific example gives us a concrete way to see how these abstract ideas play out in a physical system.
So it's like taking our quantum ruler and actually using it to measure something specific.
Exactly. And to do that, They employ a very powerful mathematical technique called analytic continuation.
Analytic continuation, that's where things start to get really complex, pun intended. Can you explain what that is and why it's needed here?
Well, think of it like this. We have functions that are defined for real variables. But to really get a handle on the quantum world, we need to extend these functions into the realm of complex variables. That's what analytic continuation does. It's like taking a function defined on a line and extending it to a whole plane.
A whole new dimension to play with.
Precisely. And by doing this, we gain access to a whole new set of mathematical tools and insights.
So it's like we're equipping ourselves with more powerful mathematical binoculars to peer deeper into the quantum world.
Exactly. And that's what allows them to calculate the Petz-Rényi relative entropy in the specific scenario and ultimately reveal its sensitivity to both classical and quantum aspects of the system.
But before we get into those specifics, I think it's a good point to pause and let our listener absorb all this foundational information. We've covered a lot of ground, and it's quite dense material.
Agreed. We'll delve into the calculations and implications in our next segment. But for now, let's give everyone a chance to digest these concepts. Welcome back.
All right, ready to dive back in.
Absolutely. I think our listener is eager to see these concepts in action, to see how we actually calculate this Petz-Rényi relative entropy.
Exactly. We've laid the groundwork. Now it's time to get our hands dirty with some calculations.
And the authors, they don't disappoint. They take us step by step through the process for a specific scenario, a free scalar field in a Minkowski wedge.
Right, that Minkowski wedge. It's our playground for this calculation.
And the key tool they use, the one that unlocks the door to these calculations, is analytic continuation. Remember, that's how we extend our functions to the complex plane.
Right, it's like upgrading our mathematical toolbox to handle the intricacies of the quantum world.
Exactly. Now, they start by focusing on the two-point function. This is a fundamental object in quantum field theory.
Okay, two-point function. Remind us what that captures again.
It essentially describes the correlations between the field at two different space-time points. You can think of it as a measure of how much one point feels the influence of another.
So it's like a quantum communication channel between different points in space-time.
That's a great way to think about it. Now, in this case, the two-point function depends on two functions, f and g, and their arguments are coordinates that have been boosted.
Boosted. You mean they've undergone a Lorentz transformation?
Exactly, a Lorentz transformation. Remember, those are the transformations that preserve the space-time interval in special relativity, and the authors cleverly exploit a key property of these transformations.
What property is that?
The determinant of any orthochronous Lorentz transformation, it's always 1. This seemingly simple fact allows them to simplify the expression for the two-point function quite a bit.
So they're using the symmetries of space-time to their advantage. It's like finding a shortcut through a dense forest.
Exactly. And the shortcut leads them to a form where the boosting is applied to the arguments of the function themselves, not to the functions f and g directly. This is crucial for the analytic continuation.
I see. It's like rearranging the furniture to make space for something new. So how does this help with the analytic continuation?
Well, by rewriting the two-point function in this form, they pave the way for extending it to complex variables. Remember, that's the whole point of analytic continuation, to go beyond real numbers.
Right, to explore the vast landscape of the complex plane. But I imagine navigating that landscape can get pretty tricky. What are some of the challenges they encounter?
One of the big challenges is ensuring that the extended function, the one defined for complex variables, is well behaved. We don't want any mathematical inconsistencies popping up.
Right, like infinities or other nasty surprises.
Exactly. And to avoid those pitfalls, they carefully analyze the real part of the exponent in the integral expression of the two-point function.
Why the real part?
Because if that real part becomes positive, the integral could diverge. It could blow up to infinity, and that would spell trouble.
Okay, so they need to keep that real part in check. How do they do that?
They derive a very clever equation, equation 3.9, which expresses the real part of the exponent in a way that allows them to analyze its sign very carefully.
Equation 3.9. Got it. And what's the significance of that equation? What does it tell us?
It links the real part of the exponent to inner products involving vectors that encode information about the space-time coordinates, the boosting parameters, and the energy momentum of the field.
Wow, so it's connected the geometry of space-time, the Lorentz transformation, and the energy of the field, all in one equation.
Precisely. It's a beautiful example of how different concepts come together in a coherent way. And by carefully analyzing this equation, they prove that the real part of the exponent stays negative within the region they're interested in.
So they've essentially built a mathematical safety net to prevent the integral from diverging.
Exactly. They've ensured that the analytic continuation is valid and that our calculations won't lead to nonsensical results. Now, once they've established this analytic continuation of the two-point function, the next step is to use it to calculate the Petz-Rényi relative entropy.
Okay, the moment of truth. How do they do that?
They take that analytically continued two-point function and plug it into their general formula for the Petz-Rényi relative entropy.
And out pops the answer.
Well, not quite that simple, but it does lead them to an explicit expression, which is given in equation 3.Heathery. This equation captures the interplay between the classical and quantum aspects of the system.
And this is where their remarkable observation comes in, right? The fact that the Petz-Rényi relative entropy depends on both the symplectic form, which represents the classical structure, and the symmetric part of the two-point function, which is purely quantum.
Absolutely. That's one of the key takeaways of this paper. It shows that the Petz-Rényi relative entropy is a genuinely quantum measure. It's sensitive to aspects of the system that classical measures would miss entirely.
It's like having a quantum compass that can detect subtle variations in the quantum landscape that would be invisible to a classical compass.
A beautiful analogy. And to further solidify this connection to quantum mechanics, they demonstrate how the Petz-Rényi relative entropy can be derived from the concept of standard subspaces.
Ah, yes, those standard subspaces. Can you remind us how those fit into the picture?
Standard subspaces, they provide a framework for understanding localized regions in quantum field theory. And the authors show that the Petz-Rényi relative entropy can be understood in terms of the properties of these subspaces.
So it's like they're giving us multiple perspectives on the same quantum object, each revealing different facets of its structure.
Precisely. And by connecting their results to the well-established framework of standard subspaces, they're showing the robustness and significance of their findings. But they don't stop there. They go on to actually calculate the Petz-Rényi relative entropy for a specific example.
A concrete example, that's always helpful. What example do they choose?
A free, massive scalar field in the Minkowski vacuum state. It's a classic example in quantum field theory.
Okay, so they're putting their mathematical machinery to the test in a real-world scenario. What do they learn from this calculation?
This calculation allows them to demonstrate the practicality of their approach. And it reveals that the Petz-Rényi relative entropy in this case does indeed exhibit a dependence on both classical and quantum features, just as they expected.
So it's a confirmation of their earlier findings, but now in a specific physical system.
Exactly. It's one thing to have a general theory, but it's always satisfying to see it work out in a concrete example. And this example also highlights the role of the analytic continuation of the two-point function in capturing those quantum effects.
So it's all coming together beautifully. But I understand they don't just stop at the calculations. They also discuss the physical implications of their results.
You're absolutely right. They highlight the consistency of their findings with previous results, which is always a good sign. For example, they show that their expression for the Petz-Rényi relative entropy reduces to the known result for the relative entropy when a certain parameter, alpha, approaches 1.
Ah, so their theory encompasses the previous knowledge, but it also goes beyond it.
Exactly. They emphasize that unlike the relative entropy, which can sometimes be interpreted classically, the Petz-Rényi relative entropy captures genuinely quantum effects. It's a window into the weird and wonderful world of quantum mechanics.
It's like we're seeing a new layer of reality, a layer that classical physics simply cannot access.
That's a fantastic way to put it. And the beauty of this paper is that it guides us through the mathematical steps involved, so we understand the logic and the rigor behind their analysis.
It's not just presenting results, it's empowering us with the tools to understand them.
Precisely. And those tools, they can be used to explore even more fascinating questions. Now, before we move on to the final part of our deep dive, would you like to revisit any particular aspect of this calculation or discuss anything that needs further clarification?
Yeah, I think we've covered the core of the paper really well.
Yeah.
But what I find really exciting is how they point towards future research.
Oh, absolutely. They're not just content with what they found. They're already looking ahead, thinking about the next challenge.
And one of those challenges, they specifically mentioned extending their analysis to fermionic systems.
Right, fermions. They're a whole different ballgame compared to the scalar fields we've been discussing.
Yeah, I mean, for our listener who might not be as familiar, can you remind us what makes fermions so special?
Sure. So bosons, like the scalar field, they love to be in the same state. You can pack as many of them together as you want. But fermions, like electrons, they're much more solitary.
It's like they have a personal space bubble they don't want anyone to cross.
Exactly. They obey the Pauli exclusion principle, which means no two fermions can occupy the same quantum state.
And that one little rule, that exclusion principle, has profound consequences, right?
Absolutely, it shapes the entire structure of matter. Think about atoms, how the electrons are arranged in different shells around the nucleus. That's all because of the Pauli exclusion principle.
It's amazing how one simple principle can have such far-reaching effects.
It really is. And that's why extending the framework of Petz-Rényi relative entropy to fermionic systems is so exciting. It could open up a whole new world of understanding.
It's like we're taking a tool that's been honed to perfection on one type of system and applying it to a completely different beast.
Exactly. Who knows what kind of hidden patterns or unexpected connections we might uncover?
It could revolutionize our understanding of materials like superconductors, where the electrons behave in such bizarre ways.
Absolutely. And it could shed light on topological insulators, these strange materials that conduct electricity only on their surface.
The possibilities are mind-boggling. But the authors don't stop at fermions, do they? They also hint at an even bigger challenge, incorporating interactions into their framework.
Right, interactions, that's where things get really messy, really complicated.
Yeah, I mean, their analysis focused on free theories, where particles just kind of do their own thing. But in the real world, particles are constantly interacting.
It's like a giant chaotic dance floor with particles bumping into each other, exchanging energy, changing partners.
And trying to capture that complexity mathematically, that's a whole other level of difficulty.
Oh, absolutely. But if we could develop techniques to calculate quantities like the Petz-Rényi relative entropy in interacting theories, it would be a game changer.
It would allow us to understand entanglement and quantum correlations in systems much closer to those found in nature.
Exactly. Think about quantum chromodynamics, the theory that describes the strong force binding quarks together inside protons and neutrons. That's an interacting theory, and understanding entanglement in that context would be a major breakthrough.
Or condensed matter physics, where interactions between electrons give rise to all sorts of amazing phenomena.
Right. Superconductivity, superfluidity, the fractional quantum Hall effect, these are all driven by interactions. If we could apply the tools of Petz-Rényi relative entropy to these systems, who knows what we might discover?
It's like we're opening a new chapter in the story of quantum mechanics.
Exactly. And the authors, they even hint at the ultimate challenge, applying these ideas to quantum gravity.
Quantum gravity, the holy grail of physics. The quest to unify Einstein's general relativity with quantum mechanics.
The granddaddy of all challenges.
But how could this paper, which focuses on a specific type of entropy in the specific quantum field theory, possibly contribute to something as monumental as quantum gravity?
Well, one of the central mysteries of quantum gravity is the nature of space-time at the Planck scale, where quantum effects are thought to dominate.
That's the realm of the incredibly small, where space and time themselves become fuzzy and uncertain.
Exactly. And some theories suggest that space-time itself might emerge from the entanglement of fundamental degrees of freedom.
So instead of thinking of space-time as a background stage, it might be more like a fabric woven from quantum threads of entanglement.
That's one of the mind-blowing ideas being explored. And if that's true, then understanding entanglement measures like the Petz-Rényi relative entropy could be crucial for understanding the very nature of space and time.
It's amazing how something that started as a tool for comparing quantum states could potentially lead us to a deeper understanding of the universe itself.
It's a testament to the power of abstract thought and mathematical reasoning. We start with a seemingly simple question, and it can lead us to the most profound insights.
Well, this deep dive has certainly been a journey. We've explored the intricate world of Petz-Rényi relative entropy, from its mathematical foundations to its potential applications in diverse areas of physics.
It's been a real pleasure guiding our listener through this fascinating landscape.
And to our listener out there, we hope this deep dive has sparked your curiosity. We hope you'll continue to explore these ideas and maybe even contribute to this exciting field of research.
After all, the quest for knowledge is a never-ending journey. There's always more to discover, more to understand.
So keep asking questions, keep pushing the boundaries, and who knows, maybe one day you'll be the one making the next groundbreaking discovery. Until next time, keep exploring. Ever think about how entropy, that measure of disorder, well, how it changes when you get into the quantum realm?
Yeah, it gets pretty wild.
For sure.
Yeah.
Today, we're going way beyond basic thermodynamics.
Definitely beyond the basics.
We're diving deep into a paper
Oh, yeah.
that explores a unique type of relative entropy
Okay.
called Petz-Rényi
Interesting.
and how it applies to quantum field theory, or QFT for those in the know.
Right, right. It's a fascinating area. This specific paper we're looking at, it's called Petz-Rényi Relative Entropy in QFT from Modular Theory.
Catchy title.
It is. And the authors are Markus B. Fröb and Leonardo Sangaletti from the University of Leipzig.
Got it. And what are they trying to do in this paper?
Well, they're really going deep into how we can measure the, how do I put it, the quantumness of the differences between states.
Using this Petz-Rényi relative entropy.
Exactly.
Okay. Yeah. But for those of us who, maybe aren't quantum physics whizzes, what's the significance of this Petz-Rényi relative entropy? Why should we care?
Good question. It's all about understanding the fundamental nature of quantum information.
Okay.
And, how we tell the difference between quantum states. Think of it as a tool to measure how non-classical the difference between two states is.
Gotcha. Now, the paper starts by talking about Araki-Uhlmann relative entropy.
Right.
Can you give us a quick rundown of what that is and why it's important here?
Absolutely. It's kind of the foundation for everything else in the paper.
The foundation.
Yeah, it's essentially a measure of how distinguishable two quantum states are from each other.
Okay.
The authors give an equation for it, equation 1.1. It looks like this. Cessez elnerize. Might seem a bit intimidating, but it's really just describing the relative entropy between two states.
Using this relative modular Hamiltonian.
You got it, ln.
So that modular Hamiltonian acts like a quantifier of the energy difference between those states.
Exactly. It's the energy difference, but seen through a quantum lens.
Through a quantum lens. Okay.
Now, the paper goes on to introduce Petz-Rényi relative entropy.
Right.
As a kind of generalization of this formula.
A generalization. And they give a specific equation for that too, right?
Yep. Equation 1.4. It looks like this. Psi LNT.
Okay.
Here, alpha, it's a parameter. It lets us kind of fine-tune the measurement.
Fine-tune.
Yeah, of the difference between those two states, and Hus.
So you can adjust how sensitive your measurement is with this. That's pretty neat.
It is. And then they also bring up sandwiched Rényi relative entropy.
Okay.
Which is equation 1.5.
Mm-hmm.
It really highlights the fact that in quantum mechanics, the order you do things in really matters.
Because of those non-commutative quantum operators.
Exactly.
Right? So both Petz-Rényi and sandwiched-Rényi, they're both measuring the difference between states.
Right.
But they're taking into account those unique aspects of quantum operations.
Yeah.
Okay.
Yeah.
But how does any of this translate to something that we can, actually observe, something we can measure?
Well, think of relative entropy as it's telling us the probability of us misidentifying one state for another based on the measurements we take.
Oh, okay.
So the higher the relative entropy, the less likely we are to mix up those two states.
So it's like a measure of how distinguishable those states are based on what we see experimentally.
Exactly.
Makes perfect sense. Now, the paper, it goes on to do some serious mathematical derivations. You ready to tackle those?
Absolutely. Let's dive into the math.
Let's do it. Section 2.1 is where they really get down to business.
Yeah.
They really rigorously establish the properties of Petz-Rényi relative entropy.
Right.
And they start by introducing this relative Tamita operator, say, defined in equation 2.1. And this operator, it seems pretty key in modular theory.
It's a crucial one.
It's connecting those two states that we're comparing.
Right.
Modular theory seems to be playing a pretty big role here.
It is.
Can you maybe elaborate on that a bit further?
Sure. Modular theory, it's this powerful mathematical framework for understanding the relationship between states and observables in these quantum systems.
Okay.
The Tamita operator especially, it's like it's essential for defining the modular flow and the modular Hamiltonian, which are, really central to this whole paper.
Okay, so we're building on these modular theory concepts to really grasp the intricacies of Petz-Rényi relative entropy.
Yep.
What happens next in their derivation?
Well, they use the Tamita operator to establish this whole series of inequalities and bounds, leading up to equation 2.4.
2.4.
Yeah. And this equation, it lets them really explore how Petz-Rényi relative entropy changes as we adjust that difference parameter, that I.
So they're basically looking at the sensitivity of this entropy measure.
Yeah, exactly.
Why is that concept so important? The differentiability with respect to I.
Well, it's differentiability. It tells us how smoothly that entropy changes as we tweak that difference parameter. Like, think of it like finding the slope of a curve.
Okay.
It's showing you how much the entropy value changes if you make a small change in I.
Right.
So this kind of sensitivity analysis, it's really important for understanding how the entropy measure behaves.
Yeah.
And its properties.
So they're building this rigorous mathematical framework to analyze this entropy.
Exactly.
What's the next big step in their process?
The next crucial step is proving that Petz-Rényi relative entropy is always non-negative.
Non-negative.
And this is where convexity comes in.
Convexity. I remember that from calculus. How does it apply here?
So a convex function, it always curves upwards.
Right.
Equation 2.10 shows that a certain function related to the entropy, it has a second derivative that's less than or equal to 0. And that's actually the definition of a concave function, which is basically the opposite of a convex function.
So they're proving concavity to indirectly show that the entropy itself can never be negative.
That's it.
Very clever.
Each of those equations in this section, they kind of build on the one before it, adding another piece to the puzzle of understanding Petz-Rényi relative entropy.
Okay. Now, there's this concept. It's really intriguing to me. It's this analytic continuation of the modular flow.
Right.
Can you break down what that is and why is it important here?
Yeah, analytic continuation, it's like this powerful tool in complex analysis. It lets you extend the definition of a function beyond its original domain.
Okay.
So here, the authors use it to calculate the Petz-Rényi entropy for a wider range of that parameter, Ryan. They do this by first looking at the modular flow. It's described by the function ft in equation 2.11. And by extending that function to the complex plane, they can calculate the entropy for values of alpha that were initially outside the scope of that original definition.
So they're using a tool from complex analysis to unlock deeper insights into quantum entropy. That's fascinating. What comes next in the paper?
From here, they shift gears a bit. They start applying all these concepts to free bosonic quantum field theories in section 2.2.
That sounds like a whole new level of complexity.
It is, but that's where things start to get really interesting.
Well, I'm on the edge of my seat. Let's dive into the world of free bosonic QFTs.
Let's do it. Okay, so free bosonic quantum field theories. Free bosonic QFTs.
Free bosonic QFTs.
Yeah. They describe systems where particles can be created and annihilated, kind of like like what happened in the very early universe.
Wow, that sounds chaotic. How do you even start to make sense of a system like that?
It's a lot of particles popping in and out of existence.
For sure.
But there's this amazing order within all that chaos.
Okay.
The paper uses what's called the Weil algebra to describe these systems.
Weil algebra?
Yeah, they introduce it in equation 2.20.
Okay. Can you break down what this Weil algebra is? How does it help us in this context?
Sure. The Weil algebra, it gives us a way to represent these particle events, the creation and annihilation, using operators. And these operators, they're called Weil operators.
Weil operator.
Yep. And they're basically the fundamental building blocks of free bosonic QFTs.
The building blocks.
Yeah, they let us manipulate and analyze the quantum states of that field.
So we're moving from this abstract idea of entropy to like the actual world of particle physics.
Exactly.
Using these Weil operators.
And a key concept here is what's called a quasi-free state. It's defined in equation 2.21. Think of it like it's a simplified model of a quantum field.
Simplified.
But it still captures the essential features, the stuff we're interested in.
Makes it a little easier to work with.
Exactly. And it allows for some easier calculations.
Easier calculations, always good. What makes this quasi-free state so special, like mathematically?
Well, with a quasi-free state, you can define something called a bilinear form. It's denoted by O2, and it captures the correlations between the particles in the system.
So to show you how those particles, the ones constantly being created and destroyed, how they relate to each other.
Precisely. And this bilinear form is really closely connected to the two-point function of the theory.
Two-point function.
Yeah, it's a fundamental concept in quantum field theory. It tells you how the field at one point in space-time influences the field at another point.
It's amazing how all these different parts of the theory are so connected.
They are.
Where do they take this next?
Well, the authors, they want to calculate the Petz-Rényi relative entropy
Okay.
between the vacuum state, denoted by ACE, and a coherent excitation of that vacuum state. And they represent this excitation using a while operator, WF, acting on the vacuum.
So that WF, it's like a little nudge.
Hmm.
That pushes the system out of its, its lowest energy state, the vacuum.
That's a good way to think about it. And the resulting entropy, it's expressed in equation 2.23. And you'll see it brings us back to that modular operator we talked about earlier.
So we're applying these modular theory concepts to a real, specific physical situation.
Right.
What's the advantage of, of using these free theories in this context?
Free theories, they have a really specific structure,
Okay.
which makes them mathematically, a lot easier to handle. Like equation 2.24 tells us that the modular group, it acts on the while generators in a geometric way. It transforms them in a way that's consistent with the underlying space-time structure.
There's an elegance to how these ideas from different areas of physics all fit together.
It is quite elegant. And this elegance, it allows the authors to use analytic continuations, similar to what we talked about before, to come up with a nice, clear expression for the Petz-Rényi relative entropy in this particular case.
And I'm guessing that brings us to equation 2.29.
You got it. That equation gives you the entropy in terms of this function, F. Yeah, and it kind of encapsulates all the essential information about the system.
Okay. So we've gone from these abstract definitions to a formula that we can use to calculate the entropy.
Right.
In a free bosonic QFT. What kind of insights do we get from this formula?
Well, one of the big ones has to do with the difference between Petz-Rényi and Araki-Uhlmann entropy. We talked about that a bit earlier.
Right. The difference being how they deal with the non-commutativity of those quantum operators.
Exactly. And it turns out that Petz-Rényi entropy, it depends not just on the symplectic form, which is connected to the antisymmetric part of the two-point function, but also on the symmetric part. And that's different from Araki-Uhlmann entropy, which only depends on the symplectic form.
I'm not sure I follow. Can you elaborate on that?
Sure. So the symplectic form, it's present in both the classical and the quantum descriptions of the system. But the symmetric part of the two-point function, that's purely quantum.
Purely quantum.
It arises from things like the uncertainty principle.
So Petz-Rényi entropy, it's capturing aspects of quantumness that Araki-Uhlmann entropy just misses.
Exactly. It's like Petz-Rényi has a sharper lens.
A sharper lens.
Yeah, it can see finer details in the quantum world. It's sensitive to stuff that's fundamentally quantum mechanical.
This is incredible. So what happens next?
Well, they don't stop there.
Of course not.
They go on to connect this entropy to something called standard subspaces in section 2.3.
Standard subspaces.
Yeah.
Okay, what are those and how do they fit into all of this?
Standard subspaces, they provide another way to look at the modular structure of these free theories.
Another way.
Yeah. And they're really useful for calculating relative entropies.
So it's like viewing the same landscape but from a different angle.
That's a great way to put it. You gain some new insights in the process. And they actually define the Rényi entropy for a vector within a standard subspace in equation 2.34. This definition, it's closely linked to the Petz-Rényi entropy, but it's expressed in the language of standard subspaces.
So we're essentially translating our understanding of entropy into a new mathematical framework.
Exactly. And this translation helps to connect that modular operator, remember him, it keeps popping up,
right.
to the geometry of the standard subspace.
Geometry.
Yeah.
Okay, how does geometry come into play here?
Well, standard subspaces, they have a specific geometric structure.
Okay.
Determined by the inner product of the Hilbert space. And this geometric structure, it's really closely connected to how that modular operator acts. It's like, imagine the modular operator, it's shaping the standard subspace, like a sculptor molding clay.
So these abstract math concepts are like manifesting as shapes.
Yeah, it's pretty amazing.
Yeah.
And this connection, it provides this deeper understanding of the relationship between modular theory and relative entropy. It lets them use the geometric properties of those standard subspaces to analyze the entropy measure.
Okay, I think I'm ready for the grand finale. The paper wraps up with this concrete example using scalar fields in a wedge. Can you explain what a wedge is in this context?
Sure. A wedge, it's a specific region of Minkowski spacetime.
Minkowski spacetime.
Yeah, that's the spacetime of spiral relativity. It's like a wedge-shaped slice of, the spacetime fabric. And the authors are looking at a scalar field that's confined to this wedge.
A scalar field. Remind me what that is again?
A scalar field, it assigns a single numerical value to each point in space-time. Think of it like a temperature map,
Okay.
where every point has a specific temperature reading. It's the simplest type of field in quantum field theory.
Got it. So we're going from these abstract theories to a more concrete example, something we can visualize.
Right.
What happens next?
They turn to the Bizignano-Witchman theorem. It's this powerful tool in quantum field theory, and they use it to study the modular structure of the system. This theorem, it links the modular operator for the scalar field in that wedge to the boost operator, which describes how the field transforms under Lorentz transformations.
Ah, Lorentz transformations. Those are the ones that connect different reference frames in special relativity, right?
Exactly. So the modular structure of the theory, it's directly related to the fundamental symmetries of spacetime.
It's incredible how deeply connected all these ideas are.
It really is. And they use this connection to derive a specific expression for the Petz-Rényi entropy in this scenario. It's presented in equation 3.12.
Equation 3.12.
Yep. And that equation, it involves these integrals over the two-point function of the scalar field. And it shows how the entropy changes with that parameter opling.
So we've come full circle, started with these abstract definitions and ended up with a formula for a real physical system. What a journey.
It has been quite a journey. And this example, it really shows how powerful modular theory and relative entropy are for exploring the quantum nature of fields, even in the context of curved spacetime.
I'm still trying to process all of this. It's a lot.
It is. But, just when you thought it couldn't get any more complex.
Don't tell me there's more.
There is. There's a lot more out there, a whole universe of research.
Oh, no.
This paper, it's just the tip of the iceberg. But it really highlights those connections, those deep connections between quantum information theory and modular theory and quantum field theory.
I'm still trying to wrap my head around it all.
That's a lot to take in.
For those of us who aren't physicists.
Right.
What's the big takeaway here? What makes this research so important?
It shows us that the quantum world, it's full of surprises.
Surprises.
Yeah. And even these really abstract mathematical concepts like relative entropy, they have big consequences.
Consequence.
Yeah, for how we understand the universe.
Yeah.
Petz-Rényi relative entropy, it's a powerful new lens.
A lens.
Yeah, for looking at these quantum surprises.
I like that, a lens.
Yeah.
There was one thing in the paper that really stuck with me. It was that idea that that Petz-Rényi entropy, it can't be fully explained by classical physics.
Right.
Because it includes that symmetric part of the two-point function.
That's a key point. The symmetric part of that two-point function, it's like a fingerprint.
A fingerprint.
Of the quantum nature of that field. And because it's part of the Petz-Rényi entropy calculation, that tells us that this entropy, it's really capturing something unique about the quantum realm.
So it's like this hidden indicator of quantumness buried within this measure of information.
Exactly.
Makes you wonder what other quantum phenomena might be hidden in there.
Right. What other secrets might it reveal about, space and time and information in the quantum world? Those are the questions that, that drive us to keep researching.
This deep dive has been a wild ride. We've explored some pretty mind-bending concepts.
It has.
But it's really amazing to see, the beauty and the complexity of the universe.
Absolutely. There's always more to learn, more to explore, more to discover.
And that's the beauty of science, right?
Exactly.
Well, to all our listeners, thanks for joining us on this incredible journey into the world of Petz-Rényi relative entropy. We hope you found it as mind-blowing as we did.
It's been a pleasure.
Keep exploring, keep questioning, and keep driving deep into those mysteries of the universe.
Couldn't have said it better myself.
Welcome to another deep dive today. We're going to be going deep into quantum field theory.
Okay.
Exploring something called the Petz-Rényi relative entropy.
Right.
You might be familiar with entropy as a measure of disorder.
Sure.
But a particular type, reveals something uniquely quantum.
Okay.
About the systems we're looking at.
Interesting.
It's all laid out in this dense paper.
Yeah.
Petz-Rényi relative entropy in QFT from modular theory.
Okay, so if you're ready to flex those mathematical muscles.
Let's get started.
I think the best way to understand what makes Petz-Rényi relative entropy so special is to start with the Araki-Uhlmann formula for relative entropy.
Okay, so let's unpack that.
Okay.
Where do we even begin with the Araki-Uhlmann formula?
The formula itself is LR-AS, and it gives us the relative entropy between two quantum states, represented by Eck and Agogo.
Okay.
Think of it as calculating how much information distinguishes one state from the other.
Right, so it's not just about randomness, but about how different these two quantum states are from each other.
Yes.
The paper mentions this formula is a generalization of the one we use in quantum mechanics.
It is.
Can you walk us through that?
Absolutely.
Okay.
In quantum mechanics, we use the formula Trell and Rummerenes to calculate the relative entropy between two density matrices and Schack. The Araki-Uhlmann formula essentially extends this concept to the realm of quantum field theory, where we deal with states represented by vectors in a Hilbert space.
So we're taking a familiar concept from quantum mechanics.
Yes.
And applying it to the more complex world of quantum field theory.
Exactly.
Now, where does the Petz-Rényi relative entropy fit into all of this?
The Petz-Rényi relative entropy offers an alternative way to measure the distinction between two quantum states.
Okay.
The formula for it is Han1 LNTR.
There's that operameter again.
Yeah.
What exactly does it do?
Think of Hanuman as a tuning knob. It lets us adjust the sensitivity of our measurement.
Gotcha.
By varying us, we can emphasize different aspects of the difference between the two states.
Okay.
As LR approaches 1, the Petz-Rényi relative entropy actually converges to the standard relative entropy given by the Araki-Uhlmann formula.
Okay, so it's like we have this more general tool.
Exactly.
And the standard relative entropy is just a specific case of it.
Yes.
Now, the paper dives into the nitty-gritty of calculating the Petz-Rényi relative entropy.
Right.
Specifically in the context of free bosonic quantum field theories.
Okay.
Why focus on those?
Free bosonic QFTs are a great starting point because they are simpler to work with mathematically.
Okay.
They describe non-interacting particles,
Gotcha.
making the calculations more tractable.
So it's like starting with the ideal gas scenario in thermodynamics.
Exactly.
Before tackling more complex interactions.
Yes.
What are the key mathematical tools we need to handle this calculation?
The paper heavily relies on the concept of the modular operator and its analytic continuation.
Can you break down what the modular operator is and why it's so important here?
The modular operator is a mathematical object that encodes the dynamics of the system in a very specific way.
Okay.
It plays a crucial role in algebraic quantum field theory.
Okay.
And in this case, it helps us define a flow called the modular flow.
Okay.
That's essential for calculating the Petz-Rényi relative entropy.
And analytic continuation, if I remember correctly, involves extending a function beyond its original domain.
That's right.
How does that come into play?
We analytically continue the modular flow to complex values of a parameter, which in this case is often related to time or a boost. This continuation allows us to extract information about the Petz-Rényi relative entropy that wouldn't be accessible otherwise.
So we're going beyond the real world, so to speak.
Yes.
Into the complex plane to get more information.
Precisely.
Now, to get into the specifics of this calculation, the paper brings up something called the Weil algebra. What's its significance in this context?
The Weil algebra provides a framework for describing free bosonic systems mathematically.
Gotcha.
It involves operators called Weil operators, denoted by WF, which create and annihilate particles.
So they're like the building blocks of our quantum field theory, creating and destroying the particles that make up the field.
Yes.
The paper defines a specific state called the quasi-free state through its action on these Weil operators, A12 mile half.
Okay.
This state is crucial because it simplifies many of the calculations involved in deriving the Petz-Rényi relative entropy.
It does.
It sounds like this quasi-free state has some special properties.
It does.
That make it easier to work with mathematically.
Exactly.
But things get even more interesting when the paper connects the modular operator to the boost operator in a specific region of spacetime called the right wedge of Minkowski spacetime.
That's right.
Can you explain how that connection works?
This connection is a consequence of a powerful theorem known as the Bisoniano-Wichmann theorem. It essentially states that the modular flow which is generated by the modular operator,
Okay.
corresponds to boosting the system along a particular direction in spacetime, particularly in the right wedge.
So the way our system evolves under the influence of the modular operator
Yes,
is equivalent to boosting it in a certain direction.
that's right.
That's a pretty profound connection between abstract mathematical objects
It is.
and physical operation.
It is.
Absolutely. Yeah. And this connection is key to deriving an explicit formula
Yes.
for the Petz-Rényi relative entropy
Right.
in the specific example of the right wedge.
Correct.
Okay, let's dive into that derivation.
Okay.
Where do we start?
The key ingredient in this derivation is the two-point function,
Okay.
denoted by OXY.
Okay.
This function encodes the correlations between field values at different space-time points, x and y.
So it tells us how the field at one point influences the field at another point,
Exactly.
capturing the essential correlations within the quantum field.
Precisely.
The two-point function plays a central role because it allows us to explicitly calculate the action of the modular operator and its analytic continuation,
Right.
which are crucial for obtaining the Petz-Rényi relative entropy.
They are.
This is where the heavy mathematical lifting begins, right?
Yes.
We need to delve into the specific form of the two-point function
We do.
and the intricacies of its analytic continuation.
That's right. You got it. The paper provides a detailed walkthrough of these calculations, carefully analyzing the properties of the two-point function and ensuring that the analytic continuation is well-defined.
Okay.
We can definitely unpack those details further.
Let's do it.
Okay.
Let's take a closer look at the explicit form of the two-point function
All right.
and how it's used to derive the Petz-Rényi relative entropy in this specific example.
The two-point function for a free bosonic field can be expressed in terms of momentum space integrals.
Okay.
This representation is convenient because it allows us to exploit the properties of Fourier transforms and analyze the function in the frequency domain.
So we're transforming the problem from a space-time picture to a momentum picture,
Exactly.
which can often simplify calculations in quantum field theory.
That's right. The paper carefully lays out the steps involved in analytically continuing the function, FT2, to complex values of t, where tit is related to the boost parameter.
I'm guessing this analytic continuation is where things can get tricky,
It can.
as we need to ensure that the integrals involved converge
Yes,
and the extension of the function is well defined.
that's correct. You're absolutely right. The paper meticulously examines the conditions for convergence of these integrals, ensuring that the analytic continuation is mathematically sound. It's a delicate procedure that requires a deep understanding of complex analysis.
This is fascinating, but I think our listeners could use a moment to digest all of this.
Sure.
When we come back, let's continue unraveling this mathematical puzzle
Okay.
and explore the explicit formula for the Petz-Rényi relative entropy in this example.
Sounds good.
We'll pick up right where we left off and delve deeper into the fascinating world of quantum correlations and entropy.
Okay. Welcome back.
Before the break, we were discussing the intricacies of analytically continuing the two-point function
Right.
to derive the Petz-Rényi relative entropy in the right wedge of Minkowski spacetime.
Yes.
Right, we were just getting to the exciting part.
Yeah.
Can we delve into the specifics of that analytic continuation
Absolutely.
and see how it leads to the formula for the entropy?
The analytic continuation of the two-point function involves extending it from real values of the boost parameter to complex values. This process is essential because the Petz-Rényi relative entropy is defined in terms of complex powers of the modular operator, which are intimately connected to the boost operator. In this specific example.
So we're essentially taking this function, which describes correlations in the real spacetime, and extending it to a more abstract mathematical realm.
Exactly.
Where we can access information about the entropy.
That's a great way to put it. The paper meticulously outlines the steps involved in this analytic continuation. It starts by expressing the two-point function in terms of a contour integral in the complex plane.
A contour integral involves integrating a function along a specific path in the complex plane.
That's right.
Why is that necessary here?
It's necessary because the analytic continuation is not always straightforward.
Great.
There might be singularities or branch cuts in the complex plane that we need to navigate carefully.
Gotcha.
The contour integral allows us to define the continuation unambiguously,
Okay.
ensuring that it's mathematically consistent.
So it's like we're drawing a map of the complex plane.
Yes.
And choosing a safe route to avoid any mathematical hazards. What happens once we have this contour integral representation of the two-point function?
The next step is to deform the contour of integration.
Okay.
This deformation is crucial because it allows us to relate the integral to the properties of the modular operator
Okay.
and its complex powers.
I'm starting to see how this all ties together.
Yeah.
By manipulating the contour integral,
Yes.
we're essentially connecting the two-point function, which describes correlations in the field,
Exactly.
to the modular operator, which governs the system's evolution
That's right.
and ultimately leads to the entropy.
Precisely.
The paper provides a detailed justification for the contour deformation,
It does.
ensuring that it doesn't change the value of the integral,
Correct.
while making it possible to extract the relevant information about the entropy.
Yes.
This is some pretty intricate mathematical maneuvering.
It is.
Could you walk us through the specific steps involved in deforming the contour
Sure.
and how it leads to the formula for the Petz-Rényi relative entropy?
The contour deformation involves carefully shifting the path of integration in the complex plane,
Okay.
taking into account any poles or branch cuts that might be present. The goal is to express the integral in terms of quantities that are directly related to the modular operator and its complex powers.
And how do we make that connection to the modular operator?
The key insight is that the complex powers of the modular operator can be represented in terms of integrals involving the boost operator.
Okay.
Remember, the Bisoniano-Witchman theorem establishes a connection between the modular flow and boosts in the right wedge.
Right. So by relating the contour integral to the boost operator,
Yes.
we're essentially bringing in the modular operator through the back door.
Precisely. The paper then carefully manipulates the integral using properties of complex analysis and the specific form of the two-point function
Right.
to arrive at an explicit formula for the Petz-Rényi relative entropy.
And what does that formula look like?
The formula itself is quite involved, but it essentially expresses the entropy in terms of the parameter, the two-point function,
Okay.
and quantities related to the boost operator.
Gotcha.
It demonstrates how the entropy depends on both the correlations in the field and the specific geometric features of the right wedge.
This is fascinating,
Yeah.
but I'm starting to feel a bit overwhelmed with all the technical details.
Sure.
Can you summarize the key takeaway from this derivation for us?
The key takeaway is that the Petz-Rényi relative entropy in this specific example can be explicitly calculated
Okay.
by carefully analyzing the properties of the two-point function and its analytic continuation.
Okay.
The formula reveals a deep connection between the entropy,
Okay.
the correlations in the quantum field, and the geometry of spacetime.
That's a pretty profound insight.
It is.
It highlights how the abstract mathematical concept of entropy is intimately linked to the physical properties of the system
Absolutely.
and the structure of space-time itself.
And this connection has far-reaching implications for our understanding of quantum field theory,
Okay.
especially in the context of entanglement and black hole thermodynamics.
Speaking of entanglement, I remember the paper mentioning that Petz-Rényi relative entropy could be a powerful tool for studying entanglement
It is.
in quantum field theories.
Yeah.
Could you elaborate on that a bit?
Entanglement is one of the most intriguing and counterintuitive features of quantum mechanics.
Okay.
It describes a situation where two or more quantum systems become correlated in a way that cannot be explained by classical physics.
Right. It's like these systems are linked in a spooky way, even when they're physically separated.
Exactly.
How does Petz-Rényi relative entropy help us understand this spooky action at a distance?
One way to quantify entanglement is through a concept called entanglement entropy.
Okay.
This entropy essentially measures the degree of entanglement between two subsystems.
Okay.
Petz-Rényi relative entropy offers a way to generalize this concept, providing a more refined tool for characterizing entanglement.
So it's like we have this more powerful lens to zoom in on the subtle nuances of entanglement.
Precisely.
Can you give us a specific example of how this might work in practice?
Imagine dividing a quantum field into two regions.
Okay.
You can use the Petz-Rényi relative entropy to calculate the entanglement entropy
Okay.
between these regions.
Gotcha.
Quantifying how strongly they are entangled,
Okay.
the parameter allows us to fine-tune our measurement,
Okay.
probing different aspects of the entanglement structure.
That's really cool.
Yeah,
By adjusting this parameter,
right.
we can gain a deeper understanding of the different ways these quantum fields can be intertwined.
Exactly.
What are some of the potential applications of this in quantum field theory?
One area where it could be particularly useful is in studying the entanglement structure of black holes.
Okay.
Black holes are thought to possess a high degree of entanglement
Okay.
between their interior and exterior regions.
Hmm.
And Petz-Rényi relative entropy could provide a valuable tool for quantifying this entanglement and exploring its implications for black hole thermodynamics.
That's a pretty mind-blowing concept.
It is.
Using this entropy measure, we might be able to peer into the quantum secrets of black holes
Yeah,
and gain a better understanding of how they store information.
it's possible.
This is all incredibly fascinating, but I think our listeners could probably use another short break to process all this information.
Sure.
When we return, let's explore the potential of Petz-Rényi relative entropy to revolutionize our understanding of the quantum world
Okay.
and its most mysterious phenomena.
I'm looking forward to it.
We'll continue this deep dive into the fascinating interplay between entropy,
Right.
entanglement,
Yeah.
and the fundamental nature of reality.
Sounds good.
Welcome back to our deep dive into Petz-Rényi relative entropy in quantum field theory. We've covered a lot of ground, exploring its mathematical foundations and its potential for shedding light on entanglement in quantum fields and even black holes.
And remember, what makes this type of entropy so fascinating is its ability to quantify the quantumness of a system, something that classical entropy can't quite capture.
Right, it's not just about randomness, but about how much a system's behavior deviates from what we'd expect classically. Can you give us a concrete example of how this quantumness manifests in the context of Petz-Rényi relative entropy?
Let's go back to our example of the free scalar field in the right wedge of Minkowski spacetime. We saw how the Petz-Rényi relative entropy in this case depends not only on the symplectic form of classical geometric object, but also on the symmetric part of the two-point function.
And that two-point function, if I recall correctly, captures the correlations between field values at different points, essentially telling us how the field at one point influences the field at another.
Exactly. And these correlations are fundamentally quantum in nature. They arise from the fact that the field can exist in a superposition of different states, something that's not allowed in classical physics.
So the Petz-Rényi relative entropy is picking up on these subtle quantum correlations and giving us a measure of how quantum the system is. It's quantifying the degree to which the system's behavior breaks free from classical expectations.
Precisely. Now, the paper also mentions the possibility of extending this analysis to fermionic quantum field theories.
Fermionic QFTs describe particles like electrons and quarks, which follow different rules than bosons. What new insights might we gain by applying the Petz-Rényi relative entropy to these types of systems?
Extending the analysis to fermionic QFTs could reveal a whole new layer of complexity in the quantum behavior of matter. We might gain a deeper understanding of entanglement in systems of electrons or quarks, which could have implications for fields like superconductivity and the behavior of matter under extreme conditions.
That's incredibly exciting. It's like we're opening up a new frontier in our exploration of the quantum world. And speaking of frontiers, we can't forget the potential connection to black hole thermodynamics.
Black holes are still shrouded in mystery, but we know they possess entropy, the Beakenstein-Hawking entropy, which is proportional to the area of their event horizon. This entropy is thought to be connected to the quantum information trapped inside the black hole.
So could Petz-Rényi relative entropy provide us with a new way to understand this mysterious black hole entropy?
That's one of the most tantalizing prospects of this research. It could offer a way to quantify the quantum correlations between the interior and exterior of a black hole, potentially providing insights into the nature of black hole information and its relationship to the fundamental laws of physics.
This has been an incredible journey. We started with an abstract mathematical concept and ended up delving into the deepest mysteries of the universe.
It's amazing how powerful mathematics can be as a tool for exploring the nature of reality.
And for our listeners who have journeyed with us to the depths of quantum field theory, we want to leave you with a final thought. If Petz-Rényi relative entropy can quantify the quantumness of a system, does that mean there's a sharp boundary between the quantum and classical worlds? Or is it more of a blurry transition?
That's a profound question that physicists are still wrestling with. Perhaps further exploration of Petz-Rényi relative entropy and other tools from quantum information theory will help us map out this intriguing landscape and better understand where the quantum realm ends and the classical world begins.
Thank you for joining us on this deep dive. We encourage you to explore the resources linked in the show notes and continue your own journey into the fascinating world of quantum field theory. Until next time, keep seeking knowledge and questioning the boundaries of what we know. Welcome to the Deep Dive. Today, we're going deep into
Quantum field theory.
quantum field theory, exploring this fascinating concept of Petz-Rényi relative entropy. We've got this great paper by Markus B. Fröb and Leonardo Sangaletti to guide us. They've got some really interesting work on how to calculate this type of entropy in the context of quantum field theory, using tools from modular theory.
Yes, it's a really elegant approach. It's quite a dense paper.
It is.
But I think we can unpack it together and get some really valuable insights.
I'm all for that. Now, before we get lost in the math, maybe we can start with a bit of a refresher. For our listeners who may not be totally familiar with it, what exactly is Petz-Rényi relative entropy? How is it different from the regular relative entropy we often encounter in quantum information theory?
That's a great place to start. So you can think of Petz-Rényi relative entropy as like a generalization of the usual relative entropy. It's a way to measure how different two quantum states are, but it gives us a more refined and nuanced perspective than the standard relative entropy.
Okay, I'm intrigued. Can you give us an example of why this refined perspective matters? When would we need to go beyond the usual relative entropy?
Well, imagine you're trying to study the entanglement properties of a complex quantum system. The usual relative entropy might tell you that two states are entangled. But Petz-Rényi relative entropy can give you a much more detailed picture of how entangled they are. It can reveal subtle differences in the entanglement structure that would otherwise be hidden.
So it's like we're upgrading our entanglement detection toolkit. Instead of just a basic yes or no answer, we're getting a more sophisticated measurement that reveals the finer details.
Exactly. And what's especially cool about Petz-Rényi relative entropy is that it's deeply connected to the mathematical structure of quantum field theory, particularly through the concept of modular theory.
Modular theory. Always a favorite. But seriously, for those of us who haven't delved into its depths, can you give us a quick overview of how modular theory comes into play here?
Of course. Modular theory is a powerful mathematical framework that helps us understand the algebraic structure of quantum systems, particularly in the context of quantum field theory. It provides a way to associate operators with certain subregions of spacetime and to study how these operators relate to each other.
And how does that connect to entropy?
Well, one of the key insights of modular theory is that there's a special operator called the modular operator that's intimately connected to the concept of entropy. This operator captures information about the local structure of a quantum state, and it turns out to be crucial for understanding how entropy behaves in quantum field theory.
So Fröb and Sangaletti are basically using this modular operator as a tool to calculate Petz-Rényi relative entropy.
Precisely. They build on a classic result called the Araki-Uhlmann formula, which relates relative entropy to the expectation value of a certain operator called the relative modular Hamiltonian.
Okay, and I'm guessing the relative part refers to the fact that we're comparing two different states.
Exactly. We're essentially asking, how much does the modular Hamiltonian change when we go from one state to another? And the answer to that question is closely tied to the relative entropy between those states.
Fascinating. So they're extending this Araki-Uhlmann formula to the realm of Petz-Rényi relative entropy. What new challenges arise when they make that leap?
One of the key challenges is that Petz-Rényi relative entropy is defined in terms of the powers of the modular operator. To calculate these powers, Fröb and Sangaletti introduce a clever technique called analytic continuation of the modular flow.
Ooh, that sounds intriguing. Can you unpack that a bit? What does it mean to analytically continue the modular flow?
Imagine you have a quantum system evolving in time. That evolution is governed by the modular operator. The modular flow is basically a mathematical description of how the system changes over time. Now, typically we think of time as a real number, but what if we extend time into the realm of complex numbers?
Whoa, that sounds like we're bending the rules of reality a bit. But I'm guessing there's a good reason for doing this.
There is. By extending the modular flow into the complex plane, we can gain access to information that's hidden when we restrict ourselves to real time. It's like we're using complex numbers as a magnifying glass to see the finer details of the system's evolution.
Okay, I'm starting to see how this could be useful. So by analytically continuing the modular flow, Fröb and Sangaletti can get a handle on those powers of the modular operator that they need to calculate Petz-Rényi relative entropy.
Exactly. It's a really elegant technique that allows them to bridge the gap between the abstract definition of Petz-Rényi relative entropy and concrete calculations in quantum field theory.
I love it when abstract math meets real-world physics. Now, I'm curious to see how they put all of this machinery to work in a specific example. The paper mentions something about free scalar fields in a Minkowski wedge. Can you tell us more about that?
Absolutely. In a later section, they apply their methods to a classic setup in quantum field theory, a free scalar field living in a wedge-shaped region of Minkowski spacetime. This example allows them to demonstrate the power of their approach and to derive some concrete results.
Okay, we'll definitely have to delve into that example in more detail. But before we do, let's take a closer look at the mathematical framework they've developed. The paper starts by laying out some key definitions and propositions. Want to walk us through that?
Sure. They start by reminding us of the definition of relative entropy in the context of von Neumann algebras.
Okay.
They define it as semega for log omega, where omega and CSA are states on a von Neumann algebra mathkel, and mathfrax is a set of normal states on mathkel.
And they point out that this definition is related to the relative modular operator via the Araki-Uhlmann theorem.
Yes. The Araki-Uhlmann theorem states that if omega and CXC are faithful normal states on a von Neumann algebra math call, then the relative entropy between omega and CXC is given by 6C omega and 6C orndo, where nathkz logaminga 6C, where maxc are vector representatives of omega and 6C in a Hilbert space on which math call acts, and delta is the relative modular operator.
Right. And they emphasize that they are interested in a generalization of this relative entropy.
Yes.
Namely, the Petz-Rényi relative entropy, which is defined as alpha omega 101 cup for alpha in 50.
Right.
And it can also be defined for alpha 0011 in 50 by taking limits.
They also point out that when taking the limit as alpha approaches 1, we recover the usual relative entropy.
And they mention another generalization called the sandwiched Rényi relative entropy.
Yes.
But they focus on the Petz-Rényi relative entropy for the remainder of their work.
Right.
They then lay out the structure of the paper, outlining the key steps they'll take to achieve their goal of computing Petz-Rényi relative entropy in quantum field theory. This careful signposting makes the paper very reader-friendly.
They go on to provide the definition of the relative Tomita operator, a key player in modular theory. This operator is defined in terms of two states and the algebra of observables, which, in the context of quantum field theory, is usually the algebra of fields restricted to a specific spacetime region.
Right. It's given by su phi eta, a phi plus b eta, where phi and eta are vectors in a Hilbert space, and $80 are complex numbers, such that eta is orthogonal to all vectors of the form, phi now.
They highlight that the relative Tomita operator is used to define two other crucial objects, the relative modular conjugation and the relative modular operator delta.
And they remind us that the relative modular operator is defined to be delta phi gas.
Then they start proving several properties of the Petz-Rényi relative entropy, which, as you recall, is defined as the logarithm of a particular spectral integral involving the relative modular operator.
Yes. The first thing they tackle is showing that the Petz-Rényi relative entropy, as defined in their paper, is well defined for a range of values of a parameter alpha.
And they meticulously demonstrate that the spectral integral is uniformly bounded, ensuring its continuity as a function of this parameter. They go through the detailed steps involved in taking derivatives of this integral, proving that these derivatives can be computed inside the integral. This sets the stage for further mathematical manipulations they'll be doing later on.
Okay, so they've laid a solid foundation by establishing the well-definedness of Petz-Rényi relative entropy in this setting. What's next on their mathematical agenda?
Well, next they establish some key properties of this entropy, specifically its non-negativity and monotonicity as a function of the parameter alpha.
Ah, those are important properties to have. Can you elaborate on how they prove those?
Sure. To prove non-negativity, they show that the integrand of the spectral integral defining the Petz-Rényi relative entropy is non-negative. This follows directly from the properties of the relative modular operator and the parameter alpha.
And for monotonicity, I'm guessing they show that the derivative of the entropy with respect to alpha is non-negative.
Precisely. They calculate the derivative explicitly and demonstrate that it can be expressed in terms of a certain integral that's guaranteed to be non-negative due to the concavity of the logarithm function.
So by carefully analyzing the mathematical structure of the Petz-Rényi relative entropy, they're able to establish these essential properties that will be crucial for their later calculation.
Exactly. And these properties have important implications for understanding how entropy behaves in quantum systems. For example, the non-negativity of entropy is a fundamental principle in thermodynamics. And the monotonicity property tells us that as we increase the parameter alpha, the entropy can only increase or stay the same.
That makes sense. So they've established the well-definedness, non-negativity, and monotonicity of Petz-Rényi relative entropy. What other mathematical tools do they develop before diving into specific examples?
One of the key tools they introduce is the concept of analytic continuation of the modular flow. This technique is essential for calculating the powers of the modular operator, which are needed to compute the Petz-Rényi relative entropy.
Okay, I remember you mentioned this earlier, but can you remind us again how this analytic continuation works? It sounds like a pretty powerful trick.
Sure. The basic idea is to extend the domain of the modular flow from real time to complex time. The modular flow is a one-parameter group of automorphisms that describes the time evolution of the system. Typically, we think of this parameter as a real number, but we can extend it to complex values.
And what's the advantage of doing that?
By extending the flow to complex time, we can access information about the system that's not visible in real time. In particular, we can use this technique to calculate the powers of the modular operator.
I see. So it's like we're using complex numbers to unlock hidden information about the system's dynamics.
That's a great way to put it. And this technique is particularly powerful in the context of quantum field theory, where the modular flow is often intimately connected to the space-time symmetries of the theory.
Okay, so analytic continuation of the modular flow is a key tool in their arsenal. Anything else they introduce before tackling specific examples?
Yes, they also discuss the concept of standard subspaces.
Okay.
These are special subspaces of the Hilbert space that are associated with certain von Neumann algebras. They play a crucial role in modular theory and are intimately connected to the relative modular operator.
Interesting. Can you elaborate on how standard subspaces come into play?
Well, one important result is that the relative modular operator can be expressed in terms of the projection operators onto certain standard subspaces. This connection allows us to gain a deeper geometric understanding of the relative modular operator and its properties.
Okay, so standard subspaces provide a way to visualize and understand the action of the relative modular operator in a more concrete way.
Precisely. And by studying the properties of these subspaces, we can gain insights into the structure of the von Neumann algebra and the states that it represents.
This is all fascinating stuff. It seems like Fröb and Sangaletti have developed a powerful mathematical framework for understanding Petz-Rényi relative entropy in the context of quantum field theory. I'm eager to see how they apply this framework to specific examples.
Me too. They've laid a solid mathematical foundation.
Yeah.
And I'm sure their examples will illuminate the beauty and power of their approach.
Let's dive into those examples then. We'll pick up where we left off in the next part of our deep dive.
Welcome back to our deep dive into the world of Petz-Rényi relative entropy. Last time, we laid the groundwork by exploring the mathematical framework developed by Fröb and Sangaletti, particularly in the context of free bosonic quantum field theories. Are you ready to see how those abstract concepts translate into concrete results?
Absolutely. I'm eager to see how they apply their methods to a specific example.
Yeah.
In the last part, you mentioned something about free scalar fields and a Minkowski wedge. What's so special about that particular setup?
It's a classic scenario in quantum field theory that allows for some really elegant calculations. A Minkowski wedge is basically a region of spacetime that's bounded by two light rays. Think of it like a slice of pizza extending infinitely in both directions.
Okay, I can picture that. And why is this wedge so interesting for studying entropy?
Well, one of the key features of the Minkowski wedge is that it has a very special symmetry called boost invariance. This means that the laws of physics are the same, no matter how fast you're moving along the direction of the wedge.
Boost invariance. Interesting. So how does this symmetry tie into the calculation of Petz-Rényi relative entropy?
The beauty of this setup is that the boost invariance of the wedge allows us to apply a powerful theorem from algebraic quantum field theory called the Bezzonino-Wichmann theorem. This theorem tells us that the modular operator for the algebra of observables localized within the wedge is simply related to the generator of boost transformations.
Wait, so we can connect the modular operator, which is key to calculating entropy, to the boost symmetry of the wedge. That seems like a pretty significant simplification.
It is. It allows us to explicitly calculate the action of the modular operator on the fields within the wedge, which is essential for computing the Petz-Rényi relative entropy.
Okay, I'm starting to see how the pieces fit together. So they're using the boost invariance of the wedge and the Bosaniano-Uhlmann theorem to simplify the calculation of the modular operator, which then feeds into their formula for Petz-Rényi relative entropy.
Exactly. It's a really elegant application of deep theoretical results to a concrete physical setting.
I love it when theory and practice come together so beautifully. Now, I'm curious to see how they actually perform these calculations. Can you walk us through some of the key steps?
Sure. In section 2.3, they first define the right wedge, $2A, as the set of all points $6 in MathP plus 1 such that 6 by lot war.
Okay, so that's the formal definition of our pizza slice, so to speak. What do they do with this wedge?
They consider the while algebra WR of observables localized in the right wedge, and a state omega on the full while algebra mathcal, which is obtained by restricting the vacuum state omega dollars on mathcal.
Got it. So they're looking at the vacuum state, which is the simplest and most symmetric state in quantum field theory, and restricting it to this wedge-shaped region.
Right, and now the key is that they can use the Bosaniano-Uhlmann theorem to get a handle on the modular operator for this restricted state. The theorem tells us that the modular automorphism group associated with the pair lay, math call omega, is given by the boost transformations in the $6 one direction.
So they're leveraging that boost symmetry we talked about earlier. How does that help them specifically?
Well, because they know how boost transformations act on the fields, they can explicitly write down the action of the modular operator on the whale operators, which are the basic building blocks of the theory.
Okay, so they're using the symmetry of the wedge to explicitly calculate the action of the modular operator. That seems like a major win.
It is, and once they have the modular operator, they can calculate its powers, which are needed to compute the Petz-Rényi relative entropy.
So it's all coming together now. They've cleverly used the geometry of the wedge and the power of the Bosaniano-Uhlmann theorem to simplify a potentially very complicated calculation.
Exactly. But there's still more work to be done. Remember, the formula for Petz-Rényi relative entropy involves a spectral integral, which can be quite tricky to evaluate.
Right. I'm sure those integrals aren't for the faint of heart. How do they tackle that challenge?
They employ a technique called analytic continuation, which we discussed in the previous section. Remember, this involves extending the domain of a function from real values to complex values.
Okay, I'm starting to get a feel for why analytic continuation is so powerful. It's like we're expanding our mathematical toolbox to include these new complex dimensions.
Exactly. And in this case, they use analytic continuation to evaluate the two-point function of the scalar field, which is a key ingredient in their formula for Petz-Rényi relative entropy.
The two-point function. Can you remind us what that is and why it's so important?
The two-point function essentially tells us how the field at one point in spacetime is correlated with the field at another point. It's a fundamental object in quantum field theory that captures the statistical properties of the field.
Okay, so it's a measure of the field's fluctuations or correlations over spacetime. And how does analytic continuation help them deal with this two-point function?
Well, the two-point function, when expressed in terms of momentum space, involves an integral. And to evaluate this integral, they need to analytically continue it to a region of the complex plane where it converges.
So they're manipulating the integral using complex analysis to make it well-behaved and easier to calculate.
Precisely. And once they have the analytic continuation of the two-point function, they can plug it into their formula for Petz-Rényi relative entropy and obtain an explicit expression.
Wow, so they've managed to obtain an explicit formula for the Petz-Rényi relative entropy of a free scalar field in a Minkowski wedge. That's quite an accomplishment.
It is, and their result is quite elegant. It shows a clear dependence on the mass of the scalar field and the geometry of the wedge.
And I'm guessing they checked that their result makes sense in various limits. For example, does it reduce to the usual relative entropy when the parameter alpha approaches 1?
Yes, they carefully verify that their formula has the correct limiting behavior. They show that as alpha approaches 1, their expression reduces to the known result for the relative entropy of a scalar field in a wedge, which was calculated previously using other methods.
That's reassuring. It gives us confidence that their approach is consistent with previous work.
And it highlights the power of their method. They've managed to generalize the calculation of relative entropy to the Petz-Rényi case, which provides a more refined and nuanced measure of the difference between quantum states.
Okay, so they've successfully tackled this concrete example and obtained some interesting results. Is there anything else they explore in this section before moving on?
Yes, they also delve into the connection between Petz-Rényi relative entropy and standard subspaces, which we briefly touched upon earlier. Remember, standard subspaces are these special subspaces of the Hilbert space that are closely related to the modular operator.
Right. I remember you saying that they provide a way to visualize and understand the action of the modular operator.
Yeah.
How do they connect this to the entropy calculation?
They showed that the Petz-Rényi relative entropy can be expressed in terms of the modular operator associated with a particular standard subspace. This connection provides a deeper geometric understanding of the entropy and reveals its close ties to the algebraic structure of the theory.
So by bringing in standard subspaces, they're adding another layer of insight into the meaning and interpretation of Petz-Rényi relative entropy.
Exactly. It's like they're illuminating the concept from multiple angles, revealing its rich mathematical structure and its connections to different aspects of quantum field theory.
This is all incredibly fascinating. I'm really impressed by the depth and elegance of their approach. They've managed to weave together so many different threads from modular theory, analytic continuation, and quantum field theory to shed new light on this fundamental concept of entropy.
I agree. It's a testament to the power of mathematical tools to illuminate the deepest mysteries of the quantum world.
Well, we've covered a lot of ground in this section, exploring the specifics of their calculations and the insights they've gained from this concrete example. I'm curious to hear what conclusions they draw from their work and what directions they suggest for future research.
Me too. Let's move on to the final part of our deep dive and see what they have to say about the broader implications of their findings. Welcome back to the final part of our deep dive into the fascinating world of Petz-Rényi relative entropy. We've delved into the mathematical framework and explored how Fröb and Sangaletti applied their methods to the concrete example of a free scalar field in a Minkowski wedge. Now I'm eager to hear their thoughts on the broader implications of their findings and what directions they suggest for future research.
Me too. They've done some impressive work uncovering these deep connections between modular theory, analytic continuation, and quantum field theory. I'm excited to see what big picture takeaways they offer.
Well, they start section 4 by summarizing their key accomplishments, highlighting that they've established a positivity, monotonicity, and boundedness of Petz-Rényi relative entropy in the context of quantum field theory.
Right, and they remind us that for unitary excitations of a common state, calculating this entropy can be significantly simplified by using the modular Hamiltonian of that common state.
Exactly. And they reiterate the crucial role of analytic continuation of the modular flow in performing these calculations. It's like they've given us this powerful new lens to examine the dynamics of quantum systems.
And they emphasize again how, in the case of free bosonic quantum field theories, the Petz-Rényi relative entropy can be expressed solely in terms of the two-point function, capturing both its symmetric and antisymmetric parts.
Yes, and they highlight that this dependence on both parts of the two-point function really sets the Petz-Rényi relative entropy apart from the usual Araki-Uhlmann relative entropy. It shows that the Petz-Rényi relative entropy is sensitive to genuinely quantum aspects of the theory that go beyond the classical picture.
It's like we're seeing deeper into the quantum realm, uncovering subtleties that were previously hidden from view.
Exactly. They then briefly revisit the concrete example of the free massive scalar field in the Minkowski wedge, reminding us that they were able to explicitly calculate the Petz-Rényi relative entropy in that scenario.
And they point out that their result nicely agrees with previous calculations for the Araki-Uhlmann relative entropy in the appropriate limit, which gives us confidence in their approach.
Right. It's always good to have those consistency checks.
Yeah.
Now let's move on to the exciting part. What directions do they propose for future research?
Yes, I'm eager to hear what new avenues they suggest exploring. Given how much ground they've covered in this paper, I can only imagine the possibilities.
Well, one natural extension they suggest is to apply their methods to fermionic quantum field theories. Remember, fermions are particles like electrons that obey a different kind of statistics than bosons.
Right, fermions are those quirky particles that like to keep their distance from each other, unlike bosons, which are happy to pile on top of each other.
Exactly. And because of this different statistical behavior, fermionic systems often exhibit unique and intriguing entanglement properties that could be revealed through the lens of Petz-Rényi relative entropy.
I can see how that would be a fruitful area of research. It's like opening up a whole new world of quantum phenomena to explore.
Another direction they suggest is to explore the implications of their findings for quantum information theory, particularly in the context of quantum field theory.
Ah, yes, bridging the gap between abstract theoretical frameworks and potential real-world applications.
Precisely. They suggest that their work could provide new insights into the nature of entanglement in quantum field theories, which could have implications for things like quantum computing and communication.
It's amazing to think how these seemingly abstract mathematical concepts could one day lead to technological breakthroughs.
And finally, they leave us with a really tantalizing open question.
Ooh, I love a good open question. What is it?
They ask, what other hidden facets of the quantum world might be revealed through the lens of Petz-Rényi relative entropy?
That's a great question to ponder. It seems we've only just begun to explore the full potential of this powerful concept.
I agree. This paper has opened up new avenues for understanding the subtleties of quantum entropy and its connection to the fundamental structure of quantum field theory. And it really makes you wonder what other mysteries are out there waiting to be unraveled.
It's a reminder that even in the most abstract theoretical frameworks, there's always more to discover, deeper connections to uncover, and the potential for groundbreaking insights that could reshape our understanding of the universe.
Well said. It's been a pleasure diving deep into this fascinating topic with you. Until next time, may your curiosity continue to lead you down intriguing paths of discovery.
And may your explorations always be filled with a sense of wonder and awe at the mysteries of the quantum world. Welcome to another deep dive into the world of quantum field theory. Today, we're going to unpack a paper by Markus B. Fröb and Leonardo Sangaletti.
Ah, yes.
It's called Petz-Rényi Relative Entropy in QFT from Modular Theory.
I've read that one.
And it's a fascinating look at how we can measure the difference between quantum states, especially within specific regions of space-time.
Yeah, it's really getting at the heart of how we think about quantum information and entanglement.
Right.
We're moving beyond sort of like basic comparisons and getting a more precise, almost microscopic view of the relationship between states.
I like that analogy.
Yeah.
So the paper starts by discussing relative entropy.
Right.
Could you give us a quick refresher on that concept and why it's important?
So relative entropy is essentially a way to quantify how much information you gain about one quantum state by knowing another.
Okay.
So imagine you have two quantum states,
Right.
represented by density matrices rho and sigma.
Okay.
The relative entropy between them tells you how distinguishable they are, based on measurements you could perform.
Yeah, it's like a measure of how surprised you'd be if you thought you had one state, but it turned out to be the other.
Exactly.
Yeah.
And the paper references the Araki-Uhlmann formula for relative entropy, which uses modular Hamiltonians.
Right.
This formula is derived from, deep theoretical concepts in quantum mechanics.
Yeah.
And it provides a really robust way to calculate relative entropy in, complex quantum systems.
Yeah, the real star of the show here is this Petz-Rényi relative entropy, which the paper presents as a sort of upgrade to the standard relative entropy.
Right.
What makes it so special?
Well, the Petz-Rényi relative entropy, it introduces a parameter alpha that allows us to tune our measurement.
Okay.
It's like having a dial that lets us focus on different aspects of the relationship between quantum states.
Interesting.
By changing alpha, we can emphasize certain features of the states and gain a more nuanced understanding of their differences.
So it's a more flexible tool. That gives us a finer-grained picture of the information landscape.
Precisely. And this flexibility is particularly valuable when studying entanglement, which is, a key feature of quantum systems.
The paper then kind of delves into some of the mathematical properties of the Petz-Rényi relative entropy.
Yeah.
Can you walk us through some of the key results?
Sure. So they start by laying out, a rigorous mathematical foundation.
Right.
They define the Petz-Rényi relative entropy using a spectral integral involving the relative modular operator,
Okay.
a concept that's rooted in modular theory.
That sounds pretty heavy-duty.
It is, but they carefully demonstrate that this definition is well-behaved and consistent with our expectations for entropy measures.
Okay.
They prove that the Petz-Rényi relative entropy is always non-negative,
Yeah.
and that it increases monotonically with the parameter alpha.
Okay.
This enshows that we're dealing with, a meaningful and robust measure of information.
So it passes the mathematical sanity check, so to speak.
Exactly. And they also show that in the limit where alpha approaches 1, the Petz-Rényi relative entropy reduces to the familiar Araki-Uhlmann relative entropy.
Right.
This demonstrates a nice continuity between the generalized measure and the standard one.
That's reassuring.
Yeah.
It shows that this Petz-Rényi relative entropy isn't some exotic, disconnected concept,
Right.
but rather a natural extension of our existing understanding.
Precisely. The authors then explore the concept of unitary excitations.
Okay.
You can think of these as, specific transformations applied to a base quantum state,
Right.
like shuffling a deck of cards.
So unitary excitation mixes up the quantum state without fundamentally altering its nature.
Exactly.
Right.
And what's fascinating is that the authors demonstrate that for these unitary excitations, the Petz-Rényi relative entropy only depends on the shuffling itself.
Okay.
Not on any additional transformations we apply. This invariance simplifies the analysis and allows us to focus on the essential changes brought about by the excitation.
It's like filtering out the noise and isolating the signal.
Yeah.
Which is incredibly helpful when dealing with complex quantum systems.
Absolutely.
Okay.
Now, to connect the Petz-Rényi relative entropy to the dynamics of quantum systems, the authors introduce the concept of analytic continuation applied to the modular flow.
Can you elaborate on what analytic continuation is and why it's important here?
So imagine you have a function that's only defined for real numbers.
Right.
Analytic continuation is a technique that allows you to extend the definition of that function to complex numbers. It's like taking a map and extrapolating it to explore uncharted territory.
So we're broadening the scope of our mathematical tools to encompass a richer set of possibilities.
Precisely. And the authors demonstrate that the Petz-Rényi relative entropy can be calculated by analytically continuing a specific function related to the modular flow. This connection is crucial because the modular flow describes how quantum states evolve in time.
Right.
And by applying analytic continuation, we can gain insights into the behavior of the system in a broader domain.
That's a brilliant insight.
Yeah.
It's like we're adding a new dimension to our understanding of quantum dynamics.
Exactly.
The paper then delves into a specific scenario where both quantum states are excitations of a common base state.
Right.
What are the key takeaways from this analysis?
So the authors show that in this scenario, the Petz-Rényi relative entropy can be expressed in a simplified form that only depends on the excitation itself, just like we saw with unitary excitations.
Right.
This simplification makes the calculations more manageable and allows us to focus on the essential differences between the states.
So it's another example of how the Petz-Rényi relative entropy helps us cut through the complexity and extract meaningful information.
Exactly. And they even derive an explicit expression for the Petz-Rényi relative entropy between the vacuum state, which is like the ground state of a quantum field, and a coherent excitation of the vacuum. This formula highlights an intriguing distinction.
What's that?
The Petz-Rényi relative entropy depends on both the symmetric and antisymmetric parts of the two-point function.
Can you elaborate on the significance of this distinction?
Certainly.
The
two-point function is a mathematical object that captures correlations between different points in a quantum field. It can be split into two parts. One that's symmetric, meaning it's the same if you swap the 2 points. And one that's antisymmetric, meaning it changes sign if you swap the points. The antisymmetric part is essentially the symplectic form, which is a concept we encounter in classical physics. This part captures the classical aspects of this system.
The regular relative entropy, which is based on the symplectic form, only sees the classical side of the story.
In essence, yes. But the Petz-Rényi relative entropy goes a step further and also includes the symmetric part, which is a purely quantum contribution. This means it's sensitive to information that classical physics simply can't access. It's like the Petz-Rényi relative entropy has a special lens that allows it to see into the quantum realm in a way that the regular relative entropy can't.
That's amazing. It seems like we're really starting to unlock the secrets of quantum information with this new tool.
Yeah, it's a powerful tool.
Now, the paper also delves into the world of standard subspaces,
Right.
which sounds like we're getting into some interesting geometric territory.
Absolutely. Standard subspaces are special types of subspaces in Hilbert space,
Okay.
the mathematical arena where quantum states reside.
Right.
They have intriguing properties that connect beautifully with modular theory.
Can you give us a more concrete picture of what a standard subspace is
Yes.
and why it's relevant here?
So, imagine drawing a line in a plane.
Okay.
That line divides the plane into two regions.
Right.
Similarly, a standard subspace divides the Hilbert space in a special way.
Okay.
It's a closed, real linear subspace
Uh-huh.
that, together with its imaginary counterpart, spans the entire Hilbert space.
Okay, I'm starting to visualize it.
Good.
But how do these standard subspaces help us understand the Petz-Rényi relative entropy?
The key is that they provide a geometric way to understand the modular operator,
Okay.
which is at the heart of calculating relative entropy.
Right.
The authors show that for free theories,
Uh-huh.
like the free Masonic field we'll discuss later,
Okay.
the modular operator can be constructed directly from the standard subspace associated with the system.
So it's like the standard subspace encodes all the information we need about the modular operator.
Precisely. And that simplifies the calculation of the Petz-Rényi relative entropy considerably.
Nice.
They define something called the Rényi entropy of a vector, which is a quantity associated with a vector in the standard subspace.
Rényi entropy of a vector.
Yeah.
What does that tell us exactly?
It's a measure of how spread out the vector is within the standard subspace.
Interesting.
And it turns out to be intimately connected to the Petz-Rényi relative entropy between the vacuum state and a coherent excitation.
I see.
Yeah.
So we're using the geometry of the standard subspace to understand the information content of different quantum states.
Exactly.
Okay.
And the authors prove some important properties about this Rényi entropy of a vector.
Okay.
For instance, they show that it's always non-negative,
Good.
just like other entropy measures,
Right.
and that it increases monotonically with the parameter alpha.
Mm-hmm.
They also demonstrate that it reduces to the familiar entropy of a vector defined in previous work in the limit where alpha approaches 1.
Okay.
These properties ensure that this new entropy measure is well-behaved and fits nicely within the existing framework of quantum information theory.
This discussion of standard subspaces has been incredibly insightful. But I'm eager to see how all this theoretical machinery is put to work in a specific example.
Right.
The paper focuses on a free scalar field in a wedge-shaped region of space-time. Right.
You're absolutely right. In the next section, they'll roll up their sleeves and apply all this abstract math to a real-world scenario.
Okay.
They'll use the tools we've discussed to calculate the Petz-Rényi relative entropy for a free scalar field in Minkowski spacetime,
Okay.
focusing on a region called the right wedge.
All right.
This example will bring to life the concepts we've been exploring and demonstrate the power of the Petz-Rényi relative entropy in probing the entanglement structure of quantum fields.
This is where it gets really exciting. We're going to see how these abstract mathematical concepts translate into concrete insights about a physical system.
Exactly.
But before we dive into that, why don't we take a quick break to let everything sink in? We'll be back in a flash to continue our deep dive into the fascinating world of the Petz-Rényi relative entropy.
Sounds good.
All right, so we're back and ready to dive into that example you mentioned.
Okay.
You said they're looking at a free scalar field
Yes.
in a particular region of space-time called the right wedge.
Right.
What exactly is this right wedge,
Okay.
and why is it interesting to study?
Think of Minkowski spacetime, the flat spacetime of special relativity.
Okay.
Now imagine a region defined by all the points where the spatial coordinate by 1 is greater than the absolute value of the time coordinate x0.
Okay.
That's our right wedge.
So I'm picturing sort of like a triangular slice extending out from the origin of space-time.
Yeah, you got it.
What makes this particular shape so special for this study?
Well, it has some nice symmetry properties that make it easier to analyze.
Okay.
Plus, it's a commonly studied region in quantum field theory, especially when we're looking at entanglement entropy,
Right.
which is a measure of how much entanglement exists between a region and its complement.
So we're using this wedge as a sort of test case to see how the Petz-Rényi relative entropy helps us understand entanglement in a specific space-time region.
Exactly.
Okay.
Now, to get a handle on the entanglement in this wedge,
Yeah.
they leverage the Bisoniano-Wishman theorem.
Okay.
This theorem is a powerful tool that gives us a lot of information about the modular operator in this specific scenario.
This modular operator really is a central character in our story.
It is.
Can you remind us again what the Bisoniano-Witchman theorem tells us about it?
So in simple terms, the Bisoniano-Witchman theorem links the modular operator to a specific type of symmetry transformation called a boost.
A boost, like accelerating in a particular direction in spacetime.
Exactly.
Yeah.
In this right wedge situation, the theorem essentially tells us that the modular operator acts like a boost in the act by one direction.
Interesting.
It's like the modular operator is shifting things along that spatial axis in a specific way.
So we've got this modular operator tied to boosts.
Yeah.
We've got our wedge-shaped region.
Right.
Yeah.
And we want to calculate the Petz-Rényi relative entropy to understand the entanglement within it. What happens next?
Well, they put all the pieces together and actually perform the calculation.
Right.
They start with a two-point function, remembering that it transforms in a specific way under boosts thanks to the Bisoniano-Witchman theorem.
The two-point function, again, always lurking in the background of our quantum dance floor.
Yes.
Okay, so they've got that.
And they apply that analytic continuation technique we talked about earlier to this transformed two-point function.
Okay.
By extending it to the complex domain, they can plug it into the formula for the Petz-Rényi relative entropy.
So they're combining the symmetry properties of the system encoded in the two-point function and how it transforms under boosts with this analytic continuation trick to find a concrete expression for the entropy.
Precisely.
Wow.
It's a beautifully orchestrated combination of mathematical tools.
Oh, what's the punchline?
Okay.
What does their result tell us about the entanglement in this wedge-shaped region?
Well, they arrive at a formula for the Petz-Rényi relative entropy that depends on the parameter alpha, which we can tune to focus on different aspects of the entanglement and the specific details of the scalar field. This gives us a quantitative measure of the entanglement between the field inside the right wedge and the field outside.
So they show that the Petz-Rényi relative entropy is more than just a theoretical concept.
Right.
It can actually be calculated and used to quantify entanglement in a specific physical system.
Exactly.
That's pretty remarkable.
It is, but they don't stop there.
Okay, what else do they do?
Before diving into that calculation, they lay the theoretical groundwork by discussing free bosonic QFT in more detail.
Ah, yes, the free bosonic field we mentioned earlier.
Right.
Can you unpack that for us a bit more?
Sure. In quantum field theory, a bosonic field describes particles that follow Bose-Einstein statistics, meaning they don't mind occupying the same quantum state.
Right, okay.
A free bosonic field means that these particles don't interact with each other. It's a simplified model, but it's surprisingly powerful for understanding fundamental concepts.
So it's like a theoretical playground.
Yeah.
Where we can explore the quantum world without the messiness of interaction.
Exactly.
Okay, I like that.
Now, to describe this free bosonic field mathematically, we use something called a symmetric Fock space.
Another new term.
Yeah.
What exactly is a symmetric Fock space?
You can think of it as a giant room that can accommodate any number of bosonic particles. This room is built in a way that captures the unique characteristics of bosons. Their tendency to bunch up together within this space. We have operators called Weyl operators that act on the particles.
What do these Weyl operators do? So are they like the rules governing how particles behave?
More like choreographers directing the dance of the particles. They create and annihilate particles, move them around, and generally control their behavior within the Fock space.
So it's a very dynamic space with these Weyl operators orchestrating the movements of the particles.
Precisely. Now, the authors also introduced the concept of a quasi-free state.
Quasi-free?
Yes.
Does that mean the particles are almost free but not quite?
Not exactly. It means that the state has certain mathematical properties that make it easier to work with. You could say it's free enough to be tractable, but still captures the essential features of the quantum field.
Got it.
Okay.
And how does all of this connect to the Petz-Rényi relative entropy?
The connection lies in the modular operator. They show that for these free theories, the modular operator acts on the Weyl operators in a very specific way. It's as if the modular operator is influencing the choreography of the particles.
So the modular operator is not just a passive observer.
Right.
It's actively shaping the dynamics of the quantum field.
Precisely. And this specific action of the modular operator is what allows us to calculate the Petz-Rényi relative entropy in this setting.
Okay.
They demonstrate that it can be calculated using something called the two-point function of the quasi-free state.
Ah, the two-point function makes a comeback.
Yes, it does.
Remind me what that is again?
It's a mathematical object that captures the correlations between different points in the quantum field.
Okay.
Think of it as a measure of how much the field at one point knows about the field at another point.
So it's like a map of the interconnectedness of the quantum field.
Exactly.
Okay.
And the fact that the Petz-Rényi relative entropy can be calculated from the two-point function tells us something profound.
What's with that?
It's sensitive to the underlying structure of the quantum field,
Okay.
how different points in the field are related to each other.
It's like the Petz-Rényi relative entropy is able to see the hidden connections within the quantum world.
That's a great way to put it.
Okay.
Now, remember we talked about how the authors connect the Petz-Rényi relative entropy to the modular flow using analytic continuation.
Yes, that was a key insight.
Yes.
Can you remind us what's so important about that connection?
Okay, so the modular flow describes how quantum states evolve in time.
Right.
It's like the movie of the quantum world.
Right.
By analytically continuing a function related to the modular flow,
Uh-huh.
we can extend our view beyond the usual time domain and explore the behavior of the system in a broader context.
So we're essentially taking the quantum movie and adding extra scenes that play out in the realm of complex numbers.
That's a fantastic analogy.
Thanks.
And the authors show that by doing this, we can calculate the Petz-Rényi relative entropy in this extended domain, giving us a deeper understanding of the relationship between quantum states and their dynamics.
This is all incredibly fascinating. But I'm curious about the specific results they get for the free bosonic field.
Oh.
Do they derive any specific formulas for the Petz-Rényi relative entropy in this setting?
They do.
Okay, tell me about them.
As I mentioned earlier, they derive a nice expression for the Petz-Rényi relative entropy between the vacuum state, which is like the ground state of the quantum field, the state with the lowest possible energy,
Right.
and a coherent excitation of the vacuum.
What's a coherent excitation exactly?
You can think of it as a well-behaved ripple in the vacuum state.
Okay.
It's a specific type of excitation that preserves some of the nice properties of the vacuum, making it easier to analyze.
Got it.
Okay.
And what does this formula tell us about the Petz-Rényi relative entropy in this specific case?
It highlights a crucial point.
What's that?
The formula shows that the Petz-Rényi relative entropy in this scenario depends on both the symmetric and antisymmetric parts of the two-point function.
Right.
Yeah.
We talk about how the antisymmetric part represents the classical aspects of the system,
Right.
while the symmetric part captures something purely quantum.
Exactly.
Okay.
And this result reinforces the idea that the Petz-Rényi relative entropy is sensitive to information that's inaccessible to classical physics.
Right.
It's like it's peering into the hidden quantum layers of reality.
This is really mind-blowing stuff.
Yeah.
It's amazing how a seemingly abstract mathematical concept like the Petz-Rényi relative entropy can reveal so much about the fundamental nature of the quantum world.
I completely agree.
Yeah.
It's a testament to the power of mathematical tools in unlocking the secrets of the universe.
This discussion has been incredibly insightful.
Good.
But I'm eager to see how all of this theoretical machinery is put to work in a specific example.
Right.
We were about to dive into their calculation of the Petz-Rényi relative entropy
Right.
for the free scalar field in the right wedge, weren't we?
Yes. That's where they really bring all these ideas together.
Okay, so let's do that. All right, so let's do that. Let's dive into that calculation.
Okay, so they start by reminding us that we're working in Minkowski spacetime. Right. Which means we can use the usual coordinates time and 3 spatial dimensions.
Right.
The right wedge, as we discussed earlier, is defined by the condition that the spatial coordinate by 1 is greater than the absolute value of the time coordinate by 0.
Right. That gives us our triangular slice of spacetime.
Yeah.
What's the next step?
Well, they utilize the power of the Bisegnano-Witchman theorem,
Okay.
which, as we discussed, connects the modular operator to boosts in the by 1 direction.
Right.
This connection is key because it allows them to express the action of the modular operator on the field operators in a very specific way.
So the Bisegnano-Witchman theorem is like a bridge between the abstract world of the modular operator and the concrete world of boosts in spacetime.
Exactly.
Okay.
And they use this bridge to derive a transformation law for the two-point function under the action of the modular operator. Remember, the two-point function captures the correlations between the field at different points in spacetime.
Right. It's like a map of the interconnectedness of the field.
Yeah.
So they're showing how this map changes when we apply the modular operator,
Right.
which is essentially equivalent to performing a boost.
Precisely.
Okay.
Now, here's where the analytic continuation trick comes into play.
Right.
They analytically continue this transformed two-point function to a complex domain.
I'm picturing us taking that map of the quantum field and extending it beyond the usual boundaries of spacetime.
That's a good way to think about it.
Yeah.
And this extension to the complex domain allows them to perform some clever manipulations and ultimately plug the analytically continued two-point function into the formula for the Petz-Rényi relative entropy.
It's like they're using complex numbers to unlock hidden information within the two-point function.
Exactly.
Okay.
And by doing so, they arrive at an explicit formula for the Petz-Rényi relative entropy of the free scalar field in the right wedge.
That's amazing.
It is.
So they've actually managed to calculate this abstract quantity for a specific physical system.
Right.
What does their formula look like? And what insights does it provide?
The formula is a bit involved, but essentially it expresses the Petz-Rényi relative entropy in terms of the parameter alpha, which, as we've discussed, allows us to tune the sensitivity of our measurement,
Right.
and the quantity related to the mass of the scalar field.
So the entanglement in the right wedge is dependent on both the parameter alpha and the mass of the field itself.
Precisely.
Okay.
And this result tells us that the Petz-Rényi relative entropy is sensitive to the fundamental properties of the scalar field.
Okay.
It's not just a generic measure. It's capturing something specific about the nature of this particular field.
That's really fascinating. It highlights how the Petz-Rényi relative entropy can provide a deeper understanding of the relationship between quantum information and the physical characteristics of a system.
Absolutely.
Yeah.
And it opens up new avenues for exploring the connection between entanglement and other fundamental concepts in quantum field theory.
This deep dive has been truly enlightening. We've journeyed from the abstract world of relative entropy and modular operators to the concrete calculation of entanglement in a specific space-time region.
Right.
And we've seen how the Petz-Rényi relative entropy provides a powerful tool for probing the quantum realm and revealing information that's hidden from classical physics.
I couldn't agree more.
Yeah.
It's a testament to the ingenuity of the authors and the remarkable power of mathematical tools in illuminating the deepest mysteries of the universe.
Well said. And on that note, we've reached the end of our deep dive into the Petz-Rényi relative entropy. I hope you, our listener, have found this exploration as fascinating as we have. It's a reminder that the pursuit of knowledge is a never-ending adventure, and there are always new wonders to uncover. Until next time, keep exploring.
Keep those quantum fires burning.